In this lesson, we are going to be using the product property, quotient property, and power property for logarithms to practice expanding and condensing logarithmic expressions. In example 1, the inside of this logarithm has a product. We could think of this as a product of 2x multiplied with y. And what the product rule tells us is that if we have a product on the inside of our logarithm, then we can break that up into the sum of two separate logarithms. So we can break this up into the sum of log 2x added with log y. Now the first logarithm of log 2x still has another product on the inside of it, of 2 being multiplied with x, and so this one can break down even further to give us log 2 plus log x, and then I'll bring down the log y that we already had. And there's our final answer of this one logarithm expanded into 3 separate logarithms. Notice that we had 3 factors on the inside of the logarithm, and we're ending up with 3 logarithms in our final answer. Number 2 will work out to be the exact same way. The only difference is that this logarithm has a base of 2 instead of a base of 10. So I'll have the first log with just the 2 on the inside of it. Then I'll have the second log with just the x on the inside of it. And the third log with just the y on the inside of it. Notice that they're all added together because these were also multiplied together. The only difference was that the base of these logarithms is now 2. Because the base is 2, we can simplify the first logarithm. Log base 2 of 2 is equal to 1. Because log base 2 of 2 is asking us what is the exponent, and the exponent is 1, that goes on the base of 2 in order to give us the 2 that was on the inside of the logarithm. And then I'll just bring down the rest of what we already had in that expression. Oh, I think I had little 3's there, but I meant to have 2's. Those should all be log base 2's. In example 3, same thing, we want to break this apart. It might be tempting to start off and distribute the 3, and then you have natural log of 3a plus 3b, but there is no addition property that says how to simplify logarithms with addition on the inside. There's also no subtraction property that talks about how to simplify logarithms with subtraction on the inside. There's no rules for those. We only have rules for multiplication on the inside, division on the inside, or powers on the inside. And so rewriting this so that we then have addition on the inside is not particularly helpful. So I'm going to leave this where we can look at this as a product of 3 multiplied with a plus b. Product rule says we can separate that into natural log of 3 added with natural log of a plus b. And then notice that this one cannot simplify because that is addition on the inside, and we do not have a rule to simplify addition on the inside. In examples 4, 5, and 6, instead of the product rule, we will now be applying the quotient rule because we have division on the inside of these logarithms. Example 4, we're going to have log base 7 of z minus log base 7 of 49, and we are now subtracting these logarithms because we had division on the inside. And we can go on to simplify log base 7 of 49. It is equal to 2, because 2 is the exponent that goes on 7 to give us 49. Example 5 is going to be very similar. We're going to have log base 7 of a minus log base 7 of 14, but we cannot simplify this one because 14 is not a power of 7. It is a multiple of 7, but it's not a power of 7. In example 6, we're going to have log of 100 minus log of x plus y. Notice that whatever was in the numerator is inside the first log, the log that is positive, and whatever was in the denominator is inside the second log, the log that is negative. We can simplify this a little bit because log of 100 is equal to 2, because 2 is the exponent that goes on the base of 10 to give us 100. And we don't see the little base of 10 on that first logarithm, but we do know that it is there. In example 7, 8, and 9, we're going to be applying the power property of logarithms that says if we have something on the inside of our logarithm that has an exponent on it, then we can bring that exponent down in front of the logarithm. So for example, in number 7, this 5 that's on our exponent on x can go down in front of this logarithm to give us simply 5 ln x. In example 8, the 5 can also come down in front of this logarithm to leave us with 5 ln e. We can simplify number 8 a little bit more because remember that natural log of e is the same thing as log base e of e, which is asking us what is the exponent that goes on the base of e in order to give us e. And that is exponent is 1. So the logarithm is equal to 1. And 5 times 1 is 5. I'm going to start example 9 by rewriting the cube root of x squared as x to the 2/3. Generally speaking, the mth root of x to the n is x to the n divided by m. Now that I have this written like this, we can see the exponent of 2/3. That exponent can come down in front of this logarithm and leave us with 2/3 log x. In example 10, we are going to begin using the quotient rule because we have division on the inside of the logarithm. The quotient rule tells us we can break this up into log base 3 of 5z, subtract log base 3 of w. On the inside of the first logarithm, we have multiplication holding the 5 and the z together. Product rule says that we can break that up into a sum of logarithms, and then I'll bring down the last logarithm that we had subtracted on the end. Example 11, I'm going to again begin with the quotient rule. So I've broken this up into the difference of two logarithms, but both of these logarithms have a product on the inside, so we can apply the product rule here. So I'm breaking this up now into a sum of logarithms. But we have to be careful when we break up the second sum of logarithms because we need to make sure that we're using parentheses around that so that we know we need to distribute that negative. So in our final answer, we should ensure that all of the factors that came from the numerator, like the a and the c, are inside of logarithms that are positive in front. And the factors that came from the denominator, like the 5 and the d, are inside of logarithms that are negative. So for example, in number 12, the inside of this logarithm does not have a denominator, and so I'm not expecting any of my logarithms to be negative once I expand them. I'm not expecting to see minus signs in my answer for number 12, because we'll start off simply using the product rule. It might be tempting to start and use the power rule, but if you started with the power rule and you got 2 ln xy, and then you broke this apart, the problem is that right now the 2 is applying to the y, when the 2 was never the exponent on y. So because the 2 is not the exponent on everything that's inside that logarithm, we first need to begin with the product rule to separate the x squared from the y. Once we have the x squared separated from the y, then we can apply the power rule to just that logarithm to get our final answer. Because the 2 was only the exponent on x, it should only be in front of the logarithm with x. I'm going to start 13 by rewriting the inside of the logarithm with an x to the 2/3 in the numerator, and then I'm going to apply the quotient rule. So I am subtracting these logarithms. Notice that the second logarithm has addition on the inside, and we do not have a rule to simplify addition on the inside, so that has to stay how it is. The first logarithm has a power on the inside, and we do have a rule for expanding things that have exponents on them. Bring the exponent down in front, and don't write it there anymore like I started to. And there's our final answer. I'm going to start 14 by, instead of writing this square root, all of this is to the 1/2 power. The square root is the same thing as the 1/2 power. So the exponent of 1/2 can come down in front using the power rule. And now we have a quotient on the inside of our logarithm. So I'm going to use the quotient rule to break this up into a difference of logarithms, but we need to make sure that we're using parentheses so that we see that the 1/2 that was in front of the entire logarithm, because everything was under the square root, that coefficient of 1/2 needs to be applied to both of these logarithms. From there, we can go and break up each of these logarithms using the product rule. When you go to use the product rule, do not forget that you still have the 1/2 in front of both product rules. So notice in the second one, I do have the minus and the 1/2 there, so I do know that a negative 1/2 will be distributed to both of those logarithms on the end. I'm going to go ahead and distribute the (1/2). And I'm also going to go ahead and distribute the negative 1/2. And I just noticed that I dropped my index of 2 a long time ago. So all of these logarithms were supposed to be log base 2. And we'll see in 1 second why that is particularly important for this example. Okay, so to finish simplifying, I have a few more things to do. I have this exponent of 3 that can come down and get multiplied with that 1/2 using the power rule. So I'll go ahead and bring that down, and I'll just bring down everything that we had before that. Not forgetting to put my index of 2 on the logs. So this first logarithm here, now that we have the index fixed, log base 2 of 4 is equal to 2. Because 2 is the exponent that goes on 2 to give us 4. So the last thing we can do is multiply this 1/2 and this 2 to give us a 1. And there's our final answer. So in example 15, we're going to try to notice patterns that we've seen in how these problems work out. Hopefully we notice that things that show up in the numerator show up in positive logarithms, and things that show up in the denominator show up in negative logarithms. So when we look at this expression, we have 6 factors. 3 of those factors show up in the numerator, so 3 of those logarithms will be positive, and 3 of these factors show up in the denominator, and so 3 of these logarithms will be negative. So what we're going to do is we're going to expand this out, and when you look at this, hopefully we notice that some of those logarithms are also going to need the power rule applied to them because we have things with exponents on them. So from the 64 in the numerator, we're going to get a log base 8 of 64, which will simplify down to 2 eventually. From the x squared in the numerator, we get a positive log base 8 of x squared. Power rule says we can bring the exponent of 2 down in front of that logarithm. I don't have to bring any exponents down from the y in the numerator because it's just a log base 8 of y. Moving on to the ones in the denominator, we first have that 3 in the denominator. Because it's in the denominator, it's in a negative logarithm. So we have a negative log base 8 of 3. Followed by a negative log base 8 of z. There's nothing we can do to simplify that either. And then the last thing we have in the denominator is the w cubed. So we have a negative log base 8 of w cubed, and then we can use the power rule to bring the exponent of 3 down in front of that logarithm. And there's our final answer. Moving on, we're now going to be condensing logarithms. So instead of starting with one logarithmic expression and expanding it out to many logarithms, we're now starting with many logarithms and we will be condensing them. So in example 16, we have two logarithms that are being subtracted. Because those are being subtracted, we know that we can use the quotient rule, which tells us that we can write our answer as one logarithm with a quotient on the inside. What goes inside the numerator was what was in the first positive logarithm, and what goes in the denominator is what was in the second negative logarithm. And there's our final answer. In example 17, these logarithms are not being subtracted, they're instead being added. And there is a 4 in front of this logarithm. Because they're being added, we will be able to use the product rule. But the 4 in the front has to be sent to the exponent on the y using the power rule first. So after we use the power rule, we're left with log base 2 of z plus log base 2 of y to the 4th. And that's good because now that both of these logarithms have coefficients of 1, we're able to use the product rule to write one logarithm where we multiply the two things that were inside the old logarithms. So when we start example 18, we're again going to have to start with the power rule because we have that 3 that needs to get sent to be the exponent on the x that's inside of that natural log. And then I'll bring down everything else that's there. Our goal is to combine this into one logarithm. That logarithm will have a fraction in it, and the things that were inside the positive logarithms, like x cubed and x minus 2, will go in the numerator, and the things that were inside the negative logarithm, like 5, will go in the denominator. When we start example 19, we first need to distribute this 2 to the first two logarithms that we have there, because it's only after we have distributed it that we can see what the coefficients are to those logarithms. And once we can see the coefficients to those logarithms, then we know that we can come in and use the power rule. So we have a natural log of x with an exponent of 2 on it. And then from there we are subtracting a natural log of x squared with an exponent of 2 on it. And we're adding a natural log of z to the 9th with an exponent of 2/3 on it. And we have a minus natural log of z. So we have natural log of x squared minus natural log of x to the 4th. Because rules of exponents tell us that if we have an exponent raised to an exponent, we combine those exponents by multiplying. So going on to multiply, 9 multiplied by 2/3 is equal to 6. So this is natural log of z to the 6th. And then I have a minus natural log z. So now that we have all of these logarithms with coefficients of positive or negative 1, we can combine this into one logarithm where things that were inside of positive logarithms, like the x squared and the z to the 6th, will go in the numerator, and things that are inside of negative logarithms, like the x to the 4th and the z, will go in the denominator. And now we can simplify the inside of this to be left with z to the 5th over x squared, just using rules of exponents to combine those exponents there. Moving on to example 20, I'm going to begin by sending this negative 2 to the exponent. So there's the power rule being used here. And I did that so that all of my logarithms could have a coefficient of 1. All these logs are now positive, so I know they will combine into one big logarithm where all of these things are multiplied together, the insides from all 3 of those logarithms separately. I'm going to rewrite that first one. Make sure I put my base of 5 on these logs. I'm going to rewrite the first one so that it's not having a negative exponent. And to do that, I'm going to put it in the denominator. And now we can simplify this because x squared minus 25 factors into x plus 5, x minus 5. And the denominator of this is x plus 5 squared. So one of those x plus 5s will cancel and leave us with log base 5 of x times x minus 5 divided by x plus 5. In examples 21 through 23, we're going to use the values that they gave us for log base b of 2, log base b of 3, and log base b of 7 to evaluate new values. So in example 21, we have log base b of 21, but 21 is equal to 7 times 3. So because I can write that as a product, I can then apply the product rule to break this down into log base b of 7 plus log base b of 3. And we know that log base b of 7 is 1.2091, and log base b of 3 was given to us as 0.6826. And then we can add those to get our answer. In number 22, we have to figure out a way to come up with 9. While it might be tempting to write this as log base b of 7 plus 2, that's not a good idea because then you have addition on the inside of the logarithm, and we do not have a rule for addition on the inside of the logarithm. But we do have a rule for multiplication on the inside of the logarithm, and 3 times 3 is 9. So we could then break this up into log base b of 3 plus log base b of 3. You also could have used the power rule for number 22. We were given that log base b of 3 was 0.6826, so we could add this to itself to get our answer for number 22. And then in number 23, we simply need to apply the quotient rule, and we take our answer for log base b of 7, and we subtract our answer that we were given for log base b of 2. The last section of this lesson goes over the change of base formula. And what the change of base formula tells us is that if you have a logarithmic function written in terms of any base, you can always change it by taking a logarithm of what was on the inside of the log and dividing it by a logarithm of whatever the base was. So in this case, I chose to change the base to base 10. Because I wrote log 15 over log 7. But I also could have changed the base to natural log. Say natural log of 15 over natural log of 7. These are perhaps the most two common because there's buttons in our calculator for log and for natural log. Not every calculator has a button for, say, log base 4. But the change of base formula says we also could have evaluated this with a log base 4. So in my calculator, I'm going to just choose to type in this version. ln 15 divided by natural log of 7 gives me approximately 1.3917, rounded to 4 decimal places. And then example 25, for log base 5 of 0.3, in my calculator, I could put in log of 0.3 divided by log of 5. And that gives me negative 0.7481. As an example, Practice using your calculator and a change of base formula to evaluate log base 2 of 3.5.